Hi, this video we will start talking about torsion. And so torsion, as you can visualize, is going to twist it, right? If you have a shaft, you're going to twist it. So our goal is to figure out the shear stress in a shaft due to torsion. I mean, when you twist it, it's going to create stress, and that stress is along the surface, the cylindrical surface. So it's on that surface, it's going to be shear stress. All right, so that's going to be tau. So we're going to look into the shear stress due to the torsion, and also we're going to see what's the angle twist it is. And in order to look at, here's some example of a failure due to the torsion. And there are so many other examples in real life application. So for example, if you have some gears, that's when you're going to apply the torsions onto it. And that's going to create shear stress on the shaft. And this is another example, very visual to see the torsion, and you can see the angle of twist. And also you see the suspension, the torsion bar here. Also when you pedal on your bike, and that creates a torsion on this bar right here. Okay, so when we look at torsion, here I'm gonna skip those. We'll get back to learn the specific concept, and we're gonna look at this slide here. Torsion is gonna have a sign, positive and a negative sign. So if we're looking at internal torque, so if you cut here, if you're interested in here, if you cut over here, and you find out this internal torque is going this direction, for example, this is what going counterclockwise in this situation. So I want you to get your right hands out and 4 fingers go around this direction of the torsion. And did you realize your thumb is actually pulling outward? It's outward from this surface. If it's outward, that's going to be positive. So that's a sign convention for torsion, for internal torque. So you use your right hand, your 4-finger follow the torsion direction, and if happen your thumb is pointing outward to the surface where you cut, then that's going to be positive. Okay, so we're going to use that for some example later on. And another concept I want to go over using those slides is look at the profile of this shear stress due to torsion. And this is the profile. You notice it's linear, right? Start here, there's no shear stress. This tau is equal to 0 in the center of your shaft. And then when you start to increase the radius, you realize the torsion increases until at the outer surface of the shaft, you're going to reach the maximum of the shear. So it's a linear. And this is something you can take a moment to visualize. When you apply torsion to something, you're always going to see the maximum of the shear stress at the very outer surface, right? And this is something we can actually think about it. Outer surface gonna experience the most shear. That's where the maximum shear stress is. However, in the center of your shaft, that's when the shear stress is equal to 0. So knowing that profile, and here's the formula, shear stress due to the torsion, tau is equal to T times R over J. What's this T? T is going to be our internal torque. Okay, that's going to be our internal torque. And R is going to be the location on that cross section, that circular cross section. If that point is R, if that point of interest is at the center, then that R will be equal to 0. Put it in the equation, you know tau, the shear stress will be equal to 0. If this point of interest is at the outer surface, which is radius, that's going to be this big R, that's the radius of the circle, then you're going to experience the maximum amount of shear stress. So this point of interest could be in between 0 and the radius. And so R here, the small r, be aware it's a variable. It's where this point could be, and this point could be between 0 and outer radius. All right, so knowing that, we have a formula for shear stress, and it's internal torque over J, and J is polar moment of inertia, right? Polar moment of inertia for a circle is gonna be pi r to the fourth over 2. So those are the concepts you will be using for the next video in terms of example. And if you express that in diameter, will be pi d fourth over 32. Okay, so this is a solid shaft. But how about if you have a hollow tube, right? If it's a hollow tube, then you're going to have an outer diameter and you're going to have an inner diameter, or outer radius and inner radius. So that situation, you're going to have pi r-o, o here means outer, to the fourth minus ri, inner radius over fourth over 2. Okay. So in terms of how do we solve the shear stress, we're going to follow this procedure. We're going to go ahead using free body diagram to obtain internal torque, just like how you did for the axial loading. Then you're going to figure out how many sections. Be aware each section going to have their own internal torque. And once we figure out that, we're going to use sign convention to figure out this internal torque is positive or negative. Using right hand rule, the 4 fingers follow the direction of the torque, and if the thumb is pointing outward from the cut surface, that's going to be positive. So knowing that, and we're going to figure out the polar moment of inertia, if it's a solid shaft, or if it is if it's a solid shaft or if it's hollow, they're going to have a different moment of inertia. And then just put this formula. And be aware here, I'm using rho here. That means the small r we discussed earlier. That small r is going to be ranging from 0 to the radius of the shaft. So that would be for this concept of the torsion and the shear stress due to the torsion. Okay, so I'll see you in the next video. We're going to apply for this. All right, bye now.